this video, we will go through an introduction to matrices and matrix operations in Julia. We'll start with a vocabulary overview to get on the same page, and then we'll discuss how to make matrices and vectors in Julia and store them into variables. We'll discuss how to do operations with matrices, some of the special matrices that Julia offers built-in, and we'll close with accessing an element or range of elements in a matrix with an index expression. Note that I am running Julia from my browser, specifically with cocalc.com, as you can see, but what we go through today will work just as well if you are using Julia downloaded onto your machine or with a different browser service. So first, some quick vocab, and I might not revisit all of these terms in this video, but I do want to run through them. A matrix is a rectangular array of numbers arranged in rows and columns. The numbers inside of the matrix are each called an element, and an order of the matrix is the number of rows by the number of columns, often written as M by N. That's M as in Mary by N as in Nancy. So the matrix in this example is of the order 3 by 4. As you see, it has 3 rows, 1, 2, 3, and 4 columns, 1, 2, 3, 4. A vector is a matrix that has only one row or only one column, so they're of the order 1 by whatever or whatever by 1. I'm sorry, that would be whatever. Yeah, no, I was right the first time. 1 by whatever or whatever number of rows by 1 column. Okay, and so a matrix with only one value is a matrix of the order 1 by 1, and that is called a scalar. So how do we make a matrix in Julia? Well, I'm going to clear out this header, and I do that in this Jupyter notebook that's in CoCalc by clicking on this part and going DD on my keyboard, just so we have more space. And to make a matrix in Julia, it's quite simple. We don't need a special function or anything like that. Rather, we can use the same system we would use to make any array in Julia. At its most basic, we can make brackets, and then inside these brackets we put, separated with spaces, not with commas, the elements that'll go into the rows of our matrix. Then when we want a new row, we can separate out the new row with either a semicolon or a new line. Let's start with this. 1, 2, semicolon, 3, 4, semicolon, 5, 6. As you see, what we are getting an output when I run the cell, and I'm going to do that with Shift-Enter, or Shift-Return if you're on a Mac. And when we run the cell, we are getting, as our output, a 3 by 2 array. That is to say, 3 rows, 1, 2, 3, and 2 columns, 1, 2. And the elements are just as we had put it. The rows are separated by spaces, 1, 2, etc., and the columns, rather the new row, is designated with this semicolon. Okay? Now let's try it another way. By instead of using these semicolons, let's use enters, or return if you're on a Mac. And you can actually indent to your heart's content here, it won't matter, but as you see, now it's the same exact output, a 3 by 2 array, but within your code itself, it might look a little cleaner to you. You can, as I just referenced, you can indent it with tabs or with spaces. Won't matter. And here you see it's perfectly lined up in your code, and when you run it, it lines up as well, though you usually don't need to do that. You can actually even mix and match and have a semicolon and a new row, but honestly, you should probably pick one or the other. Okay, so let's just go back to it with the semicolons, and let's talk a little bit more about what our output is actually telling us here. So you see our output, it says int 64, comma 2. What does this mean? Int 64 is the type of data. If you are not familiar with that, do take a look at my Intro to Julia video, which goes into this concept in much more detail. We'll put in a link. It should pop up over here on the screen somewhere. In a nutshell, some data like numbers that human beings might think are the same thing are actually read by the computer quite differently. So for example, integers, these numbers without any decimal point, are different from floats, which have a decimal point. So 4 and 4.0 might, to some human being doing, a math problem, seem like the same data, but a computer considers them to be quite different from each other. And the good news is about Julia that when making a matrix, Julia will take its best guess as to what data type the elements of the matrix are supposed to be. You don't actually need to specify. For example, if we included a 4.0 here, so nothing mathematically changed, so to speak, but when we run it, you'll see that it actually now has an array with float 64 too. That is two-dimensional array of float 64, okay? And 4 and 4.0 might, to a human, look like the same data, but a computer considers them to be different from each other. One's an integer and one's a float. So when I reran this with the 4.0, you could think of this as Julia saying, they're putting in a decimal value here. They must want this to be floats in the matrix, and it acts accordingly. And in fact, everything we have, even though all of these other numbers could have, in theory, been integers, though not really, because the matrix has to all be the same data type to the best of my knowledge, they did turn everything into a float. So do keep that in mind. If you add even one float in, by default it's going to make everything a float. So you can change this data type quite easily, both the type of data, whether it's a float or an integer, for example, and the size. Here we have 64 bits, so it's quite a lot of space it's taking up. Let's return this to just integers. And these are all small numbers, so they would fit quite easily on an 8-bit architecture, so to speak. So you could do int 8 right at the beginning here. So the syntax here is kind of this data type right at the beginning, followed by your brackets. And now when we run it, you'll see that it is now a 3x2 array of integers with the 8 bits. Okay, so that's good if you don't want to take up the space of 64 bits, which is the default, at least on CoCalc. I think some other systems will have a default of 32, but you could go all the way in the other direction. The highest Julia will go is int 128, and you'll see it's going to take a little while, and there it is, and now that's 128-bit. Okay, but let's just go back to the default, which should be int 64. And one thing to note, that if you have this specified as some integer type, like int 32 or whatever, and then you try to put in a float, it's actually not going to work. It's going to give you an error. It's not going to convert this float to an integer for you. It's just going to give you an error. It's going to say, hey, you told me these are all going to be integers. What's the story? So it does have to match whatever data type you're giving it. And of course, you can also turn these into floats. If you do float 32, this time it actually will work, because all of these could be represented as floats, just with the point zeros at the end. So that actually will work. But to turn the float to the integer with the int 32, that's not going to work. Okay. So if you want to make a vector, so switching gears here to, now let's do a vector. And a vector is, you can think of it just as a matrix of just one row or just one column. You can use the same method. If it's all one row, you can just put in what you want to have in that row, just like so. Okay, 1, 2, 3, 4. And if it's a column, you can, just as before, separate out these with semicolons, like so, and it'll make it a column. Or you can also do 1, 2, 3, 4, and with these each on a new line, it'll give you the same thing. Okay, and also you can do what's called transposing these. You can change the row to a column, or the column to a row, like so, with just a single apostrophe. and that'll change it. Now what was the column is now a row, and it would work vice versa. You'll see later that we usually are going to store these into variables. In fact, we're going to get to that momentarily. So normally you would do the variable followed by that apostrophe to turn the row into the column to transpose your vector. All right, so we have a matrix in a cell. Well, that's fine. That and a nickel will get you a cup of coffee, but how do we store the matrix we made and use it later? Well, just like any other kind of data, we can store it inside a variable. And a common notation in mathematics is to have a matrix kind of denoted with a capital letter, like a capital A equals, and then, whatever your matrix is, right? And so then that'll store it, and you'll see it'll actually print out because this Jupyter Notebook is printing out the last thing in the cell. You can suppress that if you don't want to print it out with a semicolon. It'll still work, and then later you can store it. Okay, or later you can print it out. But don't feel beholden to this notation. It's actually not super idiomatic because, it has a capital letter. You could just as easily do this with, my matrix, or a more descriptive variable name. It's fine. So you'll see though, when people write out matrices by hand, they'll often use this capital A or capital B or whatever it is. So that's what we'll probably be using going forward. Okay, and so just as mentioned, you can also, if you want to see the matrix later, even if let's store it in A again. If you want to see the matrix later, you can just put in the A, but note that if you have something like 2 plus 2, all of a sudden it's only going to show you the 2 plus 2 because this Jupyter Notebook in CoCalc is just showing you the last thing, the very last thing that's in the cell. So what's someone to do? Well, you can actually use a function called display to display your matrix, and it'll show you the output as so, even if it's not the last thing in the cell. Why are we using display here and not print or println, which if you've seen the introductory Julia video, are ways to display your output, so to speak. Well, I'll show you. If we did, let's do all three. If we do print A, println A, and display A, and let's do one more. Let's do show, because that's another way. Let's actually do show A and then display A. If we run these, you'll see the output. It'll give us an output, but it's not quite in that nice matrix format that we love, right? It's not showing you it as an array with the data type and everything. So that's where display is probably the one that I would use if I were you, to just show everything you want to show in your matrix if you need to output it. Okay. And so in any event, so we have stored the matrix, and let's store a different matrix now. Let's delete all these out. And let's put in a completely different matrix here, just because I'm going to do some operations with it later. For A, I have it stored in my second monitor, and so I'm just going to copy paste it to save some time. Let's store this one into A. Actually, let's display the output. So you see, this is a nice 3x4 array. Okay, and if I just wanted to store it and I didn't want to display that yet, I can put in that semicolon. Let's do another one here for B, and let's make it B equals, and this time I'm going to put in the following. And you see this time I'm doing something a little different. I am separating out, instead of with semicolons, with new lines, and then shift enter to run the cell, and it once again makes an array. Okay, or I can put in the semicolon to just store it. Okay, so that brings me to the next thing I want to show you, which is the different operations with matrices. And you can do operations with matrices very easily by using your variables as a stand-in for our matrices, because in fact the variable, all these variables are a shorter way of saying this. Instead of writing all this out, I can just write out A. Instead of writing all this out, I can just write out B, and then I can do my operations with my matrices. So let's start with addition. If you wanted to add or subtract matrices of the same order, it's quite simple. It's just an element by element operation. So if we have our matrices A and B, which you'll see are the ones that I just stored, then all you do is you take each element and you add it, if we were adding it, which we are in this example, with its corresponding element. So you have 8 plus 4, 7 plus 6, all the way down to 29 plus negative 93, that is to say 29 minus 93. And when you add all those together, like so, you should get this output, 12, 13, 10, all the way to negative 64. Let's see. So to do that, it's just a matter of A plus B, just like so, and that's all there is to it. And you see it gives you just what you wanted, the 12, 13, 10, all the way to negative 64. In this case, the way you do it with matrices is an element by element addition, so it's a little different from multiplication, which has a couple of different operations, as we'll see later. But if you wanted to do, if you're coming from like an octave background or something, you want to do a dot plus b to really show this is element by element, you can do that too, but as you see, you actually get the same result. So if you have no idea what I'm talking about with that, honestly, I wouldn't worry about it. This is just for those who are coming from more of an octave background and might want to see it, though even in octave, it's going to be the same. So anyway, that's a little bit of a digression, but let's take a look at multiplying matrices, which is a little more complicated. There are really a few different things we might be talking about when we talk about multiplication with matrices. One is scalar multiplication, which is taking the matrix of the same order. Taking the matrix of the order 1 by 1 and multiplying it by the matrix of any order, right? And in that example, as you'll see, we have the matrix, a scalar matrix of 3, so it's really just the number 3, right? And we're multiplying it by our matrix B here. So we have 3 times our matrix B here, and all that's doing, it's just kind of, again, an element by element operation here, because we're just doing 3 times 4, 3 times 6, 3 times 8, etc., all the way to 3 times negative 93, and we end up with this figure here, which is the 12, 18, 24, all the way to negative 279. Let's see it. So that was, I believe, 3 times B, and works fine. You could also do 3 dot times B, which you'll see gives you the same result, because the dot times is an element by element versus the times is kind of a matrix by matrix. And it's actually the same result because, again, when you're doing the scalar multiplication, it's going to be akin to an element by element operation anyway. Okay, so we have 12, 18, all the way to negative 279. Should be the same, and it looks like it is. Good. So next, you can do an element by element multiplication of matrices, which is not, technically speaking, a multiplication of the matrices. It's a multiplication of the elements in the matrix, of the matrices. So you see, and that's where that dot times that I referenced earlier, this is where that comes into play. So if you have 8720, you know, our matrix A, our this is our matrix B, okay, and we're just multiplying 8 times 4, 7 times 6, okay, all the way to 29 times negative 93. It's just like addition. It's just element by element, so should be easy peasy, and it's just A, and again, dot times B. Don't forget the dot. That's what signifies it's element by element. You can think of it as what's called broadcasting if you want to Google that term, and you can learn more about what this dot is really doing. But just to keep it simple, it's this A dot times B, and it gives you this new matrix, which should be what we got here, and it is 32, 42, etc. Okay. Finally, we have matrix by matrix multiplication, and that's when we multiply an entire matrix by an entire matrix, so to speak. It is not element by element, and in fact, as you will see, the columns in the first matrix have to equal the rows in the second matrix, so we're going to need to make a new matrix here. But for now, let's just call this one matrix B, though later I'm going to save it as matrix C. So we have our matrix A, which is the same one we had before. We have our new matrix B, and we're multiplying these together, all right? And you see it's very, very tedious to do this by hand. You have 8 times 4, 7 times 6, okay? I'm sorry, no, 8 times 4, 7 times 483, 2 times 19, 0 times 11, okay? And then you add all those together, all of that just to get your first element of the new matrix, that's 3,451. And then you do the same thing over and over and over again. It's very tedious. You're taking the each element in the first row of A times each element in the first column of B, adding them together. Then the same thing again, each element in the first row of A times each element in the first row of A times each element in the second column of B, and adding all those together to get your 329. Very tedious. And it's not commutative. A times B is not the same thing as B times A, as you'll see. So it's unlike, unlike most times you see multiplication, especially through school, you'll always see, oh yeah, 2 times 4 is the same as 4 times 2. Not true when you're doing matrix by matrix. Okay? So let's see. Now we have C, and of course I did a little prep work, so let's store it. Okay, and so now we have C, so let's do A times C, and you'll see that before it took a very long time to do this by hand, and I can attest to that because I typed all this out. It took, a while to do this by hand. Julia just did it in the blink of an eye. We had 3451 all the way to negative 1607. Hopefully it's right, and it is. So that's good. And remember, C times A, it's going to give you something completely different. These are not equivalent statements. Okay. And so that's some of the operations with Julia. There's more in the documentation, but I hope that that gives you a flavor for how to do elements with how to do both the element by element and also the matrix by matrix operations with Julia. As mentioned, there's lots more that you can look into yourself, exponentiation, inverses, all kinds of things. So I do encourage you to look at that. But my goal is just to kind of show you the syntax here, and then you can take it from there. All right, so there are lots of functions that you can use to play with matrices that are in the documentation as well. But just to give you a taste of the syntax here, let's bring up A, and this time we'll just display this output just so it's handy. And let's do a few. Let's do sum and maximum, and let's do minimum as well. Okay, so sum of the matrix A, that's going to add together all of the elements in your matrix and give you its sum. In this case, let's see, it's working. I don't know why it's going so slowly, actually. Oh, there it goes. Okay, so it gave you the sum, which is 107. Okay, the maximum is going to give you the biggest number, by which I mean the number that's closest to positive infinity. Okay, so not an absolute value here, the closest to positive infinity, which is 73. Minimum, again, not an absolute value, but rather the closest to negative infinity, the smallest number in that respect, which is negative 48 in this example, which makes sense. It's actually the only negative number. Okay, and there's a lot more, so do take a look at the documentation and you'll see. The next thing I want to discuss are some of the built-in special matrices that Julia has to offer. As you'll see, I've written out several of them, though there are several more if you take a look at the documentation. I just want to show you the syntax. Let's run through some of these. as you'll see, we fed in the arguments 2, 3 for all of these, except for this one at the end, this rand at the end, where we have an additional argument, and we'll get to what that means. But we have 1s with 2, 3, and when we run it, it gives you a 2 by 3 matrix, so that's 2 rows, 3 columns, and indeed the 2, 3 stands for 2 rows, 3 columns. It's the rows, columns. Again, that M by N, M as in Mary, by N as in Nancy, notation that we saw earlier with the order. And it gives you the 2 by 3 matrix of 1s, and in this case, the 1s are floats, so it's all 1.0. Zeros is going to be similar, but with 0.0s. Rand is going to give you a 2 by 3 matrix, and when it's just written out like this, it's going to default to giving you random numbers between 0 and 1, as you'll see. So it gave you random floats between 0 and 1, but that's fine if that's what you're looking for. But if you want a specific range of values to draw from, then you can put in this first argument, your range. So the way the range works is the low number colon high number, okay? And so you have a range of 1 to 100 inclusive, and it's going to be a 2 by 3 matrix. So if we run it, now you see it has a 2 by 3 matrix of random, and the elements are random integers between 1 and 100. And how do I know they're integers? Because I see right there that they are integers. There's also other functions that you can do. I believe L type of A or something is going to tell you, the type of integer that A is, which remember is the one we had stored here. So the type of value can also just be pulled by that, or you can see it even just displayed in the output. So anyway, so that's random, and if we made it, more like between 1 and 5, you'll see, I want to get one where, oh, there we go. So see, there's some 1s in there. It's inclusive, and there's some 5s. Okay, so it's inclusive, and you can make this, much bigger. You can make it a lot of numbers, whatever you want. All right. So the last thing I want to get into, at least in this video, is accessing elements of our matrix. So I'm going to get rid of all these and keep our matrices up here. But let's go ahead and give our output of A, just so it's handy. And each of these elements in our matrix A, you can think of as having a corresponding number, an index number that designates its position in the matrix. Starting with the top left-hand corner, this element, which is just the integer 8, that has an index number of 1. And then this 9 right below it is 2. The negative 48 is 3. Then you go to the top of the next column, okay, and that's 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and so we can use the fact that these have index numbers by pulling whatever element we want from the matrix. And we can do it with the name of our matrix, in this case A, bracket, and then inside those brackets you put the index number of whatever you want to pull. So if we do 5 and then run it, you'll see it'll give us 73. And that makes sense because 1, 2, 3, 4, 5. 73 has the index number of 5, and that is indeed what we asked for, and it's what we got. Some programming languages will start at 0, but here we are starting at 1, which makes for a much more intuitive experience in my view. So do keep in mind that we are starting to count at 1 here. If you're coming from Python and you're used to NumPy arrays, then this is going to be different for you. If you're coming from like Octave, then it'll be very familiar to you. So it just depends. But you're starting at 1 for your index numbers. You can also pull an element by giving its coordinates. So for example, if we put 1, 3 in these brackets and run the cell, now you have 2, which is the first row, third column, right? 1, 2, 3, and there it is, the 2 that we got, versus if you had put, the opposite, if you had put 3, 1, now you're getting a negative 48, which makes sense because that's the third row. First column is this negative 48 right here. Okay, so you can pull it with these coordinates. You can also use a colon to access a range of elements of the matrix. So if you just do a 1 : 6, this is interesting. It'll actually give you the first 6 elements of the matrix, but note it's not going to keep the shape of the matrix. It's just going to pull them out in this kind of column list, 1 to 6. So that's 1, 2, 3, 4, 5, 6, 8, 9, negative 48, 7, 73, 2. But it just kind of smushed them all together into one big column. And that's fine, but if you wanted to get a section of your matrix maintaining the shape, and this will only work, of course, if you're actually doing it in a way that can maintain the shape, but what you can do is put as your first argument just a colon, and then as your second argument 1 : 2, and that's saying get all 3 rows, but only get the first 2 columns, right? So you see it gets all 3 rows, and so that colon is kind of just saying, hey, get everything, 1, 2, 3, but then only columns 1 to 2, 1, 2, and so you see now you have a 3 by 2 matrix. And there's quite a bit more that can be done here. I'll just show you a couple more examples. You can use the keyword end to get the range all the way to the end. So if you do like a : 2 to the end here and then run that cell. Okay, now all of a sudden what's it giving you? If we look back, it's giving you this, right? The 7, 2, 0, okay, the 3 by 3 array. What are you asking? You're asking for all 3 rows, right? That's everything, 1, 2, 3, and then columns from column 2 all the way through the end, whatever the last column happens to be. Okay, so I think that's a good spot to stop. There's quite a bit more that can be done with the matrices in Julia, but hopefully this does help you get the syntax down. Do look at the documentation for more details, but that'll conclude this video, which gave an introduction to matrices and matrix operations in Julia. If you found this video helpful, please show your support by giving it a like. It's a simple thing that really does make a difference in how many other people will be able to find and use this video, and I want to thank you very much for watching.